Okay, so let's get back to where we were last time. When we last met, we had done, or were working on, I should say, the Chinese Remainder Theorem. If I1 up to ik are ideals, then this function that basically just projects R onto every factor, R plus I1, R plus I2, R plus ik. This is a ring homomorphism with kernel. We proved that last time. In thinking about it, you can do the Chinese Remainder Theorem much more generally, but I'm going to assume a commutative ring 1 here because it smooths out the proof for the rest of it. Let's do the second statement. We've continued. So if the ideals are pairwise comaximal, then we get this here. Let me point out that for the statement, there's really nothing to prove when k equals 1, because the statement is R mod I1 is isomorphic to R mod I1, right? So I'm going to start off with k equals 2. And actually, k equals 2 is the heavy lifting case, right? Once we've got that conquered, we're in good shape. So the first thing I want to do is maximal ideals. I'm going to write I1 and I'm sorry, I'm going to write I and J instead of I1, I2. It's just more convenient. I claim first comaximal. Then okay, so I'm gonna do this first. Okay. This is always true. The product IJ is contained in I intersect J. Why is this true? Because things in here are sums of alpha beta, where alpha's here and beta's here, right? But if alpha's in I, then alpha beta is in I, right? And if beta's in J, then alpha beta is in J. So anything that you can form here is inside the intersection, right? In general, I expect the intersection to be bigger, right? So let me give you a silly example. Take the ideal consisting of the even integers, right? This is an ideal of the integers. So that's 2z. What happens when you intersect 2z with itself?
Okay.
You get 2z back. Everybody agree with that? What happens when you take the product of 2z times 2z?
Well, you lose something.
Right, now everything has to be divisible by 4, right? Because if you take the product of something that's divisible by 2 and some divisible by 2, you pick up at least a product of 4. So in this case, if you take 2z, it's strictly contained in the intersection, right? But here, these are comax. So for the other containment, we're actually going to have to use this comax. Well, since I, J are comaximal, anybody remind me what that means?
You add them together to be to the entire range.
That is correct. Right? Here's how I make my life a little bit easier. My ring contains an identity. So there exists alpha in I, beta in J, with everybody cool with that? And now I'm in good shape. Because let's be any element. Notice that X, well, right, because alpha plus beta is one. So X is X alpha plus X beta. Now, since X is in I, since X is in I, then X beta is in IJ. And since X is in J, X alpha is in IJ. Therefore, X is in IJ. So, in this case, IJ is I intersect J. So I got both containments. Okay, so that takes care of that statement. We also now we want to show also need to show that right, that's the other part of the second statement for our case K equals 2. Now, here's the way we're going to do this. I'm going to use an isomorphism here. It's tempting, is it not, to try to build a homomorphism from R mod IJ into this, right? Very tempting. Can somebody explain to me why, especially a lazy critter like myself, might not want to do such a thing? Why it might complicate my life? If I define a function from here to here, what's one of the day one things I'm gonna have to do about that function? I'm gonna have to verify it's a well-defined function, right? And no, I'd rather not do it. So what I'm going to do is I'm going to try to build a homomorphism via a function that I know is well-defined and maybe use a homomorphism theorem. We're going to define B from R into R and I'm taking advantage of the first part of the Chinese remainder theorem, which I've already proved, actually more generality, given by phi of R equals R plus I, R plus J. This is the homomorphism described in the first part of this theorem. And what do I know about this? We know phi is a homomorphism. And what else? We know that the kernel of phi is equal to I intersect J. Right? That's what the first part of the theorem said. And what we've just proved is what? We've just proved that I intersect J is equal to IJ. So this is just by our very recent work. Right? Now, what are you supposed to, last thing? I want to know, Ross, I want to show that this animal is isomorphic to this. So I know that IJ is the kernel, this homomorphism. I'd really like to show that this homomorphism is onto, right? And boy, I'm telling you, at this point, it doesn't look like, I mean, it seems like kind of a reach that this is going to be onto, right? So that the is onto. Now, this is kind of a big claim, right? Because we need to show for all X, Y, R. They are such that PR is the ordered pair X plus I, Y plus 4. I mean, this goes to R plus I, R plus J, but it's got to be equal to this somehow, right? I mean, this seems like a bit of a reach, right? Because you're supposed to get sort of the same representative in both coordinates. But here's the deal, right? These are cosets, and these ideals are co-maximal. All right. So here's what I want to do. Does everybody see why? Does everybody see why this is not clear, right? I mean, how are you going to find such an R? Well, here's since alpha, I'm sorry, since I plus J is equal to R, then there exists alpha and I, beta J, such that, make sure I get this right. Right? I agree with it. Because what is X minus Y? Well, it's just some element of R, but any element of R can be written as something at I and something at J. So I'm just going to pick this because I've done this problem and I know what's coming. I've messed around with it. Take the element X minus Y and write it as alpha plus beta. Now, let me rearrange this. X right? That's just rearranging this. And this is some element. I'm going to call this R. Because this equation right here says X minus alpha can be rewritten as Y plus beta. And of course, this is some element I'm going to call R, some element in R. Now, check out this prestidigitation. Consider phi of R. This is, by definition, but the way I've chosen this R here, cleverly, R is X minus alpha plus I, Y plus beta plus J. Well, alpha is in I. So I can absorb this into this. It's no different than this. And beta is in J. So this is X plus I, Y plus J. And how about that? So B is on to. That's the most surprising part of this. Comaximal here, very important at making this machine work. Okay, so what we have is phi from R to R on I cross R by J is onto. And we got that. And kernel of phi is IJ by our observation earlier. Therefore, by the first isomorphism theorem, the best of all isomorphism theorems, we have for the kernel of phi, it's that, and the image is R. There we go. Okay, so that's the case for K equals 2. Now assume this is the inductive hypothesis. We now assume that for some m greater than or 2, the statement holds. So we're going to assume it holds for the nth case, and now I'm going to have m plus 1 ideals. This may sound intimidating, but actually, we've already done the hard part. We'll find this to be not too bad at all. So now suppose we have m plus 1 pairwise comaximal ideals. I1, I2, M plus 1. And we're going to work our magic again. Well, so a choice. So I'm going to do my best to reduce this back to what I've already done. Because again, I'm a lazy man. I'm like JV product the rest of them. Now I've got 2 items. Oh, first question, are they comaximal? Maybe it's, I mean, I1 is comaximal to each part of that, I2, I3, etc. But is it comaximal as a product? And the answer is yes. Let me just tell this. If not, then what I would like to show is I plus J is the whole ring, right? If this is not true, I plus j is a proper ideal. Agreed? And is therefore contained in the maximum ideal. Do I agree with that? Because either I plus j is always an ideal. So two things are possible. It's either the whole ring, in which case it's co-maximum, or it's not the whole ring, in which case it's contained in some maximum ideal. Gotta love that theorem, right? Now, if that's the truth, then M contains I and M contains J. Because it contains the big one, so it has to contain the pieces that make it up. Well, but J is I2, I3, I M plus 1. Now, what's a theorem that we know about maximal ideals? A maximal ideal is also, it is also prime, right? So what you have here is M containing a product of ideals, but a maximal ideal is prime, so it must contain one of them. So M contains one. Awesome. You may tell me what the problem is with that. Don't forget, M also contains I, which is I1. Therefore, I1 and IK are contained in M. Therefore, I1 plus IK is contained in M. Therefore, R is contained in M, which is a contradiction. Now, real problem. Problems are co-maximum. So, M contains IK, and M also contains I1. It contains the sum I1 plus IK, and that contradicts the fact that they are co-maximum. So, in particular, what we have is this J and M, I and J are co-maximum. Therefore, I intersect J equals IJ. We've already shown. And this translates to I1, I2, IM plus 1, and whoops. I1 intersect I2, intersect IM, intersect IM plus 1 is equal to I1, I2, I plus 1. So there, I've got that done by induction. And the last thing I have to do is show that isomorphism. Agreed? Also note that from what we've done before, R mod IJ is isomorphic to R mod I cross R mod J. This is R mod I1, I2, IM plus 1 on this side, This is R mod I1 cross R mod I2, I3, IM plus 1. Agreed? But now, this is a product of M ideals and induction holes. So by induction, this is R mod I1, and now I can break this up by induction, R mod I2, R mod I3, R mod IM plus. And that does fine. Okay, any questions on that? Any questions? Okay. The next bit that we're going to talk about is the Chinese remainder theorem. It's powerful. You're going to want to use actually the Chinese remainder theorem when you do problem 1 of the next homework study. Here is something we talked about in the last homework set. It's kind of an introduction. And I'm going to show you why I introduced these. Well, my favorite ring, or well, one of my favorite rings is the ordinary integers. It's a prototype for everything else. Right? Can somebody name me a ring that's bigger than the integers? It contains the integers. Actually, that was the first thing on my mind, rational numbers. And how do you make the rational numbers? How do you form them?
Fractions of integers.
They're fractions of integers, right? So we do have this, yeah, this is fractions of integers, if you will. With the caveat that no zero in the denominator. Yes.
I thought it was the whole thing that the rationals were the same size as the integers or something like that. And you said it was bigger. Is that not true?
It's bigger in the sense of being a ring, right?
Oh.
As a set, they're the same size.
Oh.
Yeah.
Yeah.
So, right, we form this ring that contains the. By the way, can anybody think of any rings between them? Right? You go from the rational numbers all the way up to all the fractions. Is there anything in between? Yep.
Throw out. No. Can't throw out zero. Never mind. You need zero.
Yeah, you need zero. Let's think about. So this is a good place for me to settle. And I know it's early in the morning, but please, this is going on YouTube. So please answer this quickly. Or at least tell me you know how to do this. How do we add 1/3 and 1/7, right?
We can make it through the process.
Right. So what's the process? If you were teaching this to like a 4th grade class, what would you tell them to do?
I just multiply through and so, and then express them in terms of that as a denominator.
Okay. So that let me key on that. So the first thing you did is you looked for a common denominator, which actually was what product of these two, right? I mean, it's like sometimes when you have your basic arithmetic in grade school, they'll say, "Oh, okay, you know, what's 4/6 plus 3/4, right?" And you might say, well, okay, you simplify this or that. But one thing that you can do is you can get on the bulldozer and you can take your two denominators and multiply them, and that will be a denominator. You might be able to simplify it later, but it will certainly work for a denominator, right? And so this would be like, 21. And it would be like, yeah, right? And it's the same kind of animal if you multiply them. there's a moral to the story. If I have A over B plus C over D, or A over B times C over D, and let's not even think about simplification, what's the denominator you expect to come up with here? Right. And whatever goes on top, right? I'm not concerned about that quite at the moment. So, in a certain sense, going from the integers to the rational numbers, this is all possible fractions, right? Could you ever limit it? And how could you limit it? Well, right. So the first question is you should ask yourself, what denominators am I going to allow? With all the rational numbers, I allow every denominator because I invert the rational numbers as a field. So every integer other than 0 has to have a multiplicative inverse, right? Well, you could theoretically make a smaller set of denominators. Can anybody think of a multiplicatively closed? And that's what I mean. Notice B and D are denominators. I want BD to be a denominator. B and D are denominators. I want BD to be a denominator. Yes.
Can you fix B to something? Fix B to 3, then that would be. No, because then it goes to nothing. You multiply them. Never mind.
Right.
Okay.
You're onto something there.
A over two B,
What's that?
or A over B for any n.
Right. So look at.
Oh,
Right. So let me tackle your example first. Here's one thing that you could do. I mean, you might look at what would you let's call this ring T. This is the set of A over 2 to the n. Any integer you want, and the natural average equals 0. Right? Because, so I took your B example and I just made B equal 2. But now I realize I have to have problems because you actually put your finger on it. The problem is in this ring, you've got 1/2, for example. And so if you've got 1/2, you need to have the square of 1/2 in the ring. So no longer will 2 work for a denominator. I've got to use 4 and so forth. Notice that when I add two things of this form, A over 2n plus A prime over 2m, well, nothing else. This is 2 to the n plus m, A 2 to the m plus A prime 2 to the n. Right? And when I multiply two things of this form, this is A prime 2 to the n. Yes.
Are there any restrictions on like what that 2 could be?
No.
Could we do, this is just a thought, could we do like a fraction under there? Like 1/2 to the
Well,
n?
so you could do that and try to form the smallest ring that contains that, but you'll come back to it suffices just to look at integers.
Okay, yeah.
Here's another one that's of a different theme. How about this? What if I look at this? So what I did there is I picked a particular integer, in this case 2, and I allowed powers of 2 to be denominators, and I made another ring. This contains the integers, right? Because, for example, all you have to do is take n to be 0, and now A can go through all the integers. So this contains the integers, but it doesn't contain all. See if you can check for yourself that the fraction 1/3 cannot be written in this form. Can't do it. Okay, what about this? Here's another ring. What about all fractions that have an odd? So this is the way I'm used to adding fractions. if B and D are both odd, what can you say about BD?
So
It's also odd. Same thing for multiply. And odd. This actually forms a ring as well, but it looks like it's sort of qualitatively different than this other example because there's a lot of denominators now that are allowed. Anything, right? 5, 7, 8675309, 35, all of them are there, right? As long as it's odd. You can prove also that 1/2 is not in this room. So this is also not all of. So you introduce multiplicative sets in the homework. There's a reason. Actually, multiplicative sets reveal a lot of information in a commutative ring with identity. They reveal information about prime ideals, a surprising amount about prime ideals, and they allow us to build these rings called localizations. And localizations are basically rings of fractions, where you take some subset like this, and allow it to be denominators. What you end up doing is you turn a bunch of stuff into units. And when you're looking at a ring and trying to study what's going on in it, sometimes turning stuff into units and pushing it off to the side like that clarifies the ideal structure. For example, in this ring right here, can anybody characterize T? This is actually by this notation here, I mean the smallest ring that contains all the integers and also the fraction 1/2, right? So this is the smallest ring that contains Z and 1/2. That's essentially what this is. This one we'll talk about a little bit. This one's more complicated, but notice what this ring does is it takes the number 2, which is not a unit in the integers, right? There's no 1/2 of the integers, and it puts that 1/2 in it. It destroys that prime ideal, that maximal ideal, the ideal generated by 2, because now the ideal generated by 2 contains 1, because now you've got a 1/2 in it. Right? But it leaves the other ideals, 3, 5, so the other prime ideals. This one turns every prime in the integers, except for 2. This one, 4, 7, you have the reciprocal of 2, exception 2, and 0. So, this is an important tool for use in, well, in our setting, we won't have a commutative ring. So, I'm going to go ahead and give you all definition. Just notes here. Definition. What are the commutative ring of 1? A non-empty subset S and R is multiplicatively closed if S, T, and S implies the product of sets. We often take the convention, and we will when we start actually looking at localizations. Oftentimes, we want our multiplicatively closed sets to not contain 0. But at the outset, it does happen here. So example, if R is a commutative ring with 1, the units of R is a multiplicatively closed set. Because if U1 and U2 are units, then so is their product. Yeah. Uh, Polynomial ring. We're going to talk about this more in the class, and we introduced this in the homeworks. These are all non-zero polynomials with coefficients in R. And R is an integral domain. So think Z, for example. Then the constant polynomials, constant, we'll say constant non-zero polynomial. Form a multiple set. You'll see this actually from your homework. If you have two constant polynomials that have degree 0, their product has degree 0. Two constants multiplied together get you a constant. Example, if R is a commutative ring with 1 and P is a prime ideal, the complement of P, that is the set of elements in R that are not in P, is a multiplicative set. So actually, prime is very, very important. One of the things you prove in the homework is the complement of an ideal is always saturated. We're going to introduce that in just a moment. But it's multiplicatively closed if and only if P is a prime ideal. This is going to be central to what we do later. Here's an example of the complement of a prime ideal. Take the integers, ordinary integers. Take the prime ideal that consists of all even integers. What is the complement of that prime ideal? In the integers, if it's not even, it's right, it's odd. And remember that example I did earlier where I let the denominator to be odd? That's what's going on there. It's the complement of this particular prime ideal. Okay. Definition. That's 2 or 3. But R in a commutative ring and S a non-empty subset of R. We say S is saturated if it contains all its divisors. Let me make this statement a little bit more precise. That is, A times B is an S implies that A and B. So if the product of two things in the ring end up in that set, then both of the things the A, B that form the product have to be in the set. Okay. Any questions? What did you? We say that the ideal are beta 1 and I and R ideal. We say that this ideal is maximal with respect to the property P. Is maximal respect to property P. And P could be some property you might want your ideal to have or not have. P is prime, it's finitely generated, something like this. If I has property and ideal J such that J contains I properly does not. It's not. That's a problem. So this is what I mean when so I'm going to use this terminology something. I might say I is maximal with respect to a certain property. This property might be not finitely generated. Okay, so what do I mean if I say I has the property that it's maximal with respect to not being finitely generated? It means it has that property. It's not finitely generated. And any ideal that properly contains it is not finitely generated. So everything that contains it must be finitely generated. Here's a big one. Suppose that I intersect the multiplicatively closed set is empty, so there's no overlap, right? If I say I is maximal with respect to that property, it means that I doesn't intersect that set, but any ideal that contains it, ding, 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 hits the set. So, okay, any questions? All righty, well, I hope you all have time to roll by and see us the ice cream today. Other than that, have a good weekend and we will see you by Monday.